Alright, today we are going to look at the problem of on-chip communication. What does that involve? What are the architectures and techniques that we can use in order to accomplish on-chip communication? What are the things we are trying to communicate, and so on. So the first question that we need to answer when we are going into this is, what do we mean when we talk about on-chip communication, right? So the overall picture is, since we are talking about on-chip, it means that there is some notion of a chip within which there are certain kinds of computations going on, right? So I will call this the chip boundary, and there are, let us say, to start with, two modules, right, or two processing elements. I will call them M1 and M2, two modules that need to do some computation. Okay. Obviously, there is going to be some interaction with the outside world. There will be some input, there will be some output. These are off chip, right. So anything going outside the chip boundary is considered off chip. It is not a very clearly defined boundary. It is not very clear why you would study the on chip versus off chip things separately, except for one specific characteristic. Typically, the moment that you go off chip, outside a particular chip, it means that you are leaving the silicon wafer, you are going over metal wires, going out over a PCB trace, going into another chip over its bonding pads and so on. The capacitances that are involved over there are typically a few orders of magnitude higher than what you would have inside a single chip. So even though in principle they are all wires that are trying to get electrical signals from A to B, the magnitude of the corresponding capacitances are hugely different in the case of off chip versus on chip communication, which is why very often you will find that the problems of on chip communication and off chip communication are studied completely differently, and they have different solutions that are proposed for them also. So now what we are saying, in other words, is we are interested in this problem: how do I communicate between M1 and M2? Okay. So that is the sort of simplest form of on chip communication that we can think of, two modules that need to transfer data back and forth between each other. Okay. So at the simplest level, what we could think of is something like this. I have two modules, M1 and M2. If I want to transfer some data from M1 to M2, I need to have a set of signals that are going from M1 to M2. The very bare minimum that I need is some wires that carry the data, but in addition to that, there should be something that also allows me to indicate some form of control, right, basically to say when I am transferring data, when is the data valid, when the receiver should actually capture the data properly, and so on. Okay. That I will broadly classify as control. Okay. Now there is a third part to this, which is sometimes included under control but sometimes also considered separately, which is basically the address. If there is only M1 and M2, then there is no real addressing to be done. Either M1 is trying to talk to M2, or no one is trying to talk to M2. Okay, so there is no separate addressing that you need over here, right? But in more complex situations, that might also be required, separate addressing, in which case either we can club it under the broad category of control or consider it as a separate topic on separate bus of its own. What happens if M2 wants to send data to M1? It can't use the same wires, right? Why? Because wires are unidirectional, they are driven by a gate. Okay, if I connect a gate to a wire, whenever the output of that gate goes high, it means that the voltage on that gate is being pulled up, and whenever the output of that gate goes low, it means the voltage on that wire is going to be pulled low, right. I cannot have two gates doing the same thing to the same wire at a given time. So the simplest way to do it would be have another bus in the opposite direction, which is also got its own data and control. Okay. So this is essentially what we end up with is two point to point links, right? A communication link is essentially something that allows data to be transferred from one point to another. In this case, it is a point to point link because it starts at the sender, terminates at the receiver, no other branches, nothing else over here. This is the most trivial form of communication that you can think of. Okay. What happens if I have 3 modules? Now I have M1 over here, M2 over here, and M3. Okay. The simplest way by which I could go forward with this is have a link between M1 to M2, a corresponding reverse link from M2 to M1. Now what happens if M1 wants to talk to M3? Put another link over there. What about M2 to M3? Once again, same story, right? If I have n modules, how many links will I need? So each one, right, it's essentially going to be the total number of edges in this graph that I am going to connect, right. So at any point in time, I can choose 2 of the nodes, and there has to be a link between them. In fact, there will be 2 links, one in each direction, right. 2 into n C2. So basically equal to n into n minus 1 is basically order of n squared. Point to point links will be required in order to establish full connection between every pair of nodes in the system. Okay. There may be situations where you actually want to have something of the sort. There are obvious problems over here. One is, as I increase the number of modules, the number of wires or links that I require is going up as n square, okay, which means not only that I have large number of wires, it also means that routing them is going to become nearly impossible after a while, because I can already see that, once I go to 4, even the routing is going to become difficult in a planar geometry. I will need to have some way of going over a set of wires. I could probably go around it in this case, but as you go to larger and larger numbers, that routing essentially becomes impossible. You can no longer do it completely in a planar fashion, right. So routing will become difficult, and just the number of wires itself is going to be a problem, okay. So naturally this leads us to the question of, and on top of that, the question that you can then ask is, I have all of these wires, are they actually being used, right? I have put in all this hardware, are they actually being used, or are those wires just there because I need to be able to communicate once per day, maybe between 2 modules, right? Every time I switch on the system, once in a day I need to send some initialization information from A to B, that is all, it is never used again after that. But I have to put all those wires in place permanently over there, because if I ever need to do the communication, right. So the natural way of sort of looking at this is, forget it, this is just too inefficient, how do I share this, right. So then the moment we are talking about sharing a link, it becomes a question of how do I take a wire, right, and share it between 2 modules. In other words, I have M1 and M2, both need to be able to change the voltage on a given wire. How do I do this? Okay, because if I, let us say that I have something of this sort, I have a AND gate, I have another OR gate, and I just take both of these and connect them up over here. This can essentially lead to a short circuit, okay. So it can't be done, right. So the question then becomes, how do I do it? How do I get M1 and M2 to be able to talk, to be able to change the voltage on a given wire at the same time? There are a couple of different ways by which I can do this. One method is to say I will use a multiplexer, okay. So what happens in a multiplexer is, I have a select signal over here, and I have the data coming from M1 and I have the data coming from M2. This has now been selected, right? Either M1 or M2 has been selected based on what the value of that select signal was. The contention has been removed, or the contention has been resolved using the mux and the select. Okay. So, what is contention? It just deals with, it is a word used to signify that there are two pieces of hardware trying to drive the same wire to different voltages at the same time. There could be potentially. Using a mux, that is completely taken care of, because as long as the select signal is either 0 or 1, only one of these values can come through. Okay. Now, what happens with this is, I can also go to n cross 1 muxes, right, which will essentially have log n bits for the select, and I will have M1, M2 up to Mn with one output coming over here. Okay. So, this is also perfectly fine, it will work. Another approach that can be used is using so called tri-state logic, right. So, tri-state essentially deals with the fact that the transistors that are used in order to actually implement these logic gates, under certain conditions they can actually be made to behave like a high impedance terminal, right, meaning that for all practical purposes it is just disconnected from the rest of the circuit. Okay. The normal symbol that is used for that would be something like this. Okay. So, this is the tri-state control, this is input, this is output, this is essentially a so called tri-state buffer, right. Implementing this is actually very straightforward in CMOS logic, it is possible to do it without too much difficulty, right. You just need a couple of extra transistors on top of what you would have for a basic CMOS inverter, and you can get an inverting tri-state buffer very easily. Now, keep in mind that as far as I am concerned, as far as the person building the communication system is concerned, an inverter and a buffer are essentially the same thing. If you can tell me ahead of time that you are going to invert all the signals before you pass them on, then I can take care of that in my logic. Okay. So, implementing a tri-state buffer, inverting buffer, non-inverting buffer, all of those are very easy to do. What I can do with those is, I can then say I will take the output from M1, take the output from M2 up to Mn, and what do I do with these wires? I simply short all of them together, right. And what I do over here is, I give separate signals S1, S2 and so on up to Sn, right. Now, I need to ensure that at any time only one out of S1 to Sn is equal to 1, all the others are disabled.
So, the communication between M1 to M2 or M2?
No, sorry. So, actually that is true. In both of the cases, right, both here as well as in the next case, M1 and M2 are both trying to communicate to someone else. Okay. So, this should basically be what I will call the target, right. But yeah, M1 is not trying to communicate to M2, they cannot in the present setup. Okay. Same story here, this is directly connected to the target, right. So, as long as I ensure that either all the S1 to Sn can be off, that is also okay, at least electrically it is not a problem, right, or at most exactly one of them from S1 to Sn is equal to 1, that particular signal, whatever that M1 to M1, M2, the output of that particular module will come through to the output and will be seen by the target. Okay. So, in other words, both of these multiplexers as well as tri-state logic are two different ways by which I can implement a shared wire. Okay, that is all. At this point it is just a shared wire. It means that two of them are able to use the same wire in order to communicate with a third party. Okay, or n of them are able to communicate with the target, not between each other. Okay, but the moment I can do sharing of this sort, it should be possible to do it the other way as well. Okay. So, this basically tells us that in principle, at least from an electrical point of view, it is possible to have communication from multiple sources to a single destination. From a single source to multiple destinations is actually much easier. You just connect the same wire everywhere, right, and everybody hears it, but only one of those should respond or should do something with it, right. It is like I address somebody in the class, I call their name, everyone else can ignore what I am saying, right. So, as long as there is some way of selecting the target, the one-to-many communication is very easy to do, right. The target just needs to listen properly. Many-to-one is more tricky because electrically there is a problem. There are actually multiple wires that are coming in and need to be combined together. But now that we know how to do it, let us look at how we would take this further, right. So, in this situation what I would now say is, if I had a situation where multiple modules needed to talk to each other, I could now look at M1, M2 and M3, right, and they all go into one black box which is sitting on the side. Okay. So, all of them have two-way communication with this black box, that is all, right. And what it effectively means is that black box can now take care of setting up communications. If I want M1 to talk to M2, or if I want M1 to talk to M3 or M2 to talk to M3, all of those can be done through the black box. Okay. So, this part of it becomes a shared bus, okay, which can then set up communications between each of these pairs as required. Okay. So, now there is a little bit of terminology that comes up over here that is worth explaining. There is something called a master, and a master on a bus is something that can initiate a transaction on the bus. What is a transaction? We will get to that later, but effectively initiate communication on the bus, right. It can actually pull the values of the voltages high or low at some point without waiting for anyone else to give permission. Okay. So, this can initiate a transaction on the bus, right. The opposite of that obviously is the so called slave, which can only respond to a request that is coming from the bus, because the master is not going to talk directly to the slave. The master will send its signals, they will be intercepted by the bus will then send some signals further down to the slave, but for all practical purposes it is as good as saying the master is able to communicate with the slave. Okay. Now, once we have these two basic pieces of terminology, we can start thinking of different configurations of what a bus could look like, of what a system could look like, a system that uses this bus, right. And there are two so called degenerate configurations of this that are worth at least understanding, right. So, the two sort of trivial cases, n masters, one slave. Can you think of what this hardware configuration corresponds to. There are n different modules that have the ability to initiate a transaction on the bus, but there is only one slave whose job is only to respond. No, MUX, by the way, I mean, see, MUXes and so on are not the kind of modules that we are talking about here. They are just what we would call infrastructure IP. They are used as building blocks. It's like an adder, right? So, a MUX is for all practical purposes like an adder. It's not a complex module on its own. So, each and every one of these modules, the M1, M2 that I am drawing over here, is something that has almost certainly will require some internal state machine of its own to control its behavior, and most likely does something non-trivial. Okay? The most trivial kind of a module, the slave in some sense, is what we are actually going to use in this example, which is a memory block, right. So, one way of looking at this would simply be that I have a memory block and two CPUs. Okay. So, both of these would be masters, whereas this one would be a slave. Think about it, the memory by itself is never going to try and transfer data somewhere, right. The whole idea of a memory is it's a storage space. So, any time that somebody wants to either put data in there or get data out of it, they will make a request, right. The memory by itself is not going to volunteer information. So, it's a slave in this case, very clearly defined. If I have two different CPUs, both of them potentially at any point in time might want to read some data from the memory, therefore, they are both potential bus masters. Okay. The other case is one master, n slaves. This is also fairly easy to understand. I could just think of it as this is my CPU, this is the master, and on the other side, example peripherals, what can you think of? One is of course the memory itself. Then let us say I have a keyboard, mouse, display, Ethernet card, serial port, USB, printer, right. Any number of things are all on the other side. Okay. By default I can think of all of them as things that are slaves, in the sense that at any point in time the only one that is actually doing work or is requesting data from all of these is going to be the CPU. So, these two cases are actually fairly easy to understand, but they already illustrate two extra things that we need to sort of watch out for, right. The second case, one master n slaves, is like I said the case where there is one master and all that it needs to do is give out, as long as it mentions who it's trying to talk to. Is it trying to poll the keyboard to find out what key was pressed, or is it trying to look at the mouse to see where the mouse has moved to, or is it trying to write some data onto the screen? All of those, the CPU is the master. Okay. All that it needs is that the bus over here requires some kind of decode logic, right. And what the decode logic means is the CPU is not able to talk directly to the memory or to the keyboard. It only sends it has a standard set of connections that connect it to the bus, but the number of wires required for the keyboard peripheral versus the number of wires required for the memory unit are probably different. The bus takes care of filtering that out. It sees what is the CPU trying to do. How does it understand that? By looking at the control signals, part of which is the address bus that is put out, the address. Okay. So, like we discussed in the previous class, memory mapping essentially means that that address can now be used in order to indicate which of the peripherals I am trying to talk to. The bus looks at the address and decodes it. When I say, this is sort of anthropomorphic way of looking at it. There's nothing sitting on the bus that's actually looking at it. It's just a set of gates handing things together and deciding, okay, is there a match or not, right? But as long as the bus is able to match the address that was sent, that was put out there by the CPU, and say, okay, this corresponds to the keyboard, right? Either send some control signal to the keyboard or get data back from the keyboard so that it can be sent back to the CPU. Okay. If it was for the display, then basically take whatever is coming from the CPU, send it to the display module, etc. So the bus takes care of decoding. Okay. What happens in the other case when I had two masters and one slave? That's a bit more tricky, because even though logically it's quite simple to draw this, right, and we also figured out that yes, as long as I have tri-state logic or multiplexers, I can get multiple masters to electrically connect. I still haven't decided which one gets to talk at any given point in time. Okay. What if both the CPUs want to read from memory at the same time? Or one CPU wants to read from memory, can it be sure that the other one is not trying to use the bus at the same time? Can it just go ahead and start a conversation, or does it have to wait for something? All that essentially means that there is something called arbitration that needs to be done by the bus. Okay. So just like there are masters and slaves, the moment you have multiple masters, it means that there is something called arbitration that is required, and the moment you have multiple slaves, it means there is decoding to decide which of those slaves is being spoken to. So this business of arbitration logic, how do I decide which master gets to communicate at any given point in time, is a non-trivial problem. There are of course multiple solutions to it. You can think of simple solutions on your own. Anyway, we will go over a couple of those later.